Moving on to the next question. This is a question which was asked in most of the PhD interviews. It is like this: derive density of states of phonons for 3D, 2D, and 1D case. So here I will give a simple technique. You will see a lot of methods to derive the density of states of phonons in many textbooks, many complicated techniques, but they are not expecting that from you. What they expect is that is the method I'm going to tell. This is a simple method. This is a simple method. So what is density of states? So density of states is that number of states per unit volume per unit energy interval. So this is the simple definition for density of states. So what are phonons? Phonons are quantum of lattice vibration. A quantum of lattice vibration is called as phonon. So by device theory, the lattice vibration is compared or considered to be similar to that of a vibration of string. Okay, so if you are considering a 1D lattice of atoms, 1D lattice of atoms, so the vibration of these atoms can be considered to be similar to that of the vibration of a string. Okay, so there are many modes possible for the vibration of string, like this type of vibration, going up and down, going up and down. So this is the fundamental mode of vibration. And the other mode possible is like this. So this is the other mode of vibration possible. This is the first overtone. Second mode of vibration. This is the first overtone. Okay, here. So for this up and down type of vibration correspond to n is equal to 1, because lambda is given by 2L by n. So when n is equal to 1, lambda is equal to 2L. When n is equal to 2, lambda is equal to L, where L is the length of the string. Okay. So simply by device theory, Debye has compared the vibration of atoms, phonon, to be similar to that of the vibration of a string. So there are different modes available for atoms to vibrate, similar to that of the different modes available to the vibration of string. Like the up and down vibration correspond to n is equal to 1 mode, fundamental mode, and this red color type of vibration corresponds to n is equal to 2. So this n is actually the quantum number. So n is equal to 1 corresponds to fundamental mode, n is equal to 2 correspond to the first overtone, like that n is equal to 3, n is equal to 4 are there. Many modes of vibration are possible. Similarly, for atoms also, there is fundamental modes, first overtone, second overtone, many n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. Such modes are possible, similar to the vibration of string. Now we will be deriving the density of states based on number space. Number space is nothing but like this. Nx, ny, nz. So a particular point in this space, the coordinates will be nx, ny, nz, right? So what does this nx, ny, nz means? As I said, This n corresponds to this lambda n is equal to 2L by n. So this n, this n actually. For example, if nx is equal to 1, it means that in the lattice, if we are analyzing the lattice with respect to x direction, in a three-dimensional crystal, there will be many atoms. So when we are analyzing the atoms, okay, in the x-axis, so this is x-axis, okay, so this is the boundary. If we are considering a cube, there will be boundary along x directions, y directions, as well as z directions, right? So we are only considering now the atoms along the x-axis. Now, so the atoms can undergo vibrations like this, fundamental mode, or it can undergo first overtone, second overtone. As nx is equal to 1, it implies that the atoms along the x-axis undergo fundamental mode of vibration. If you are considering a particular point, say this one with coordinates 3, 2, 1, it means that along x-axis, the atoms along the x-axis undergo the second overtone, and the mode of vibration along for atoms lying in the y-axis is first overtone, and the atoms along the z-axis undergoes the fundamental mode of vibration. Like that, each point in the number space correspond to a quantum state in which the coordinates represents the mode of vibration the atoms are undergoing along x, y, and z direction, lying along x, y, and z direction. So I assume that you understood this concept. So this is for your understanding only. So if they ask you to derive the density of states of phonons for 3D case, 2D case, and 1D case, what you have to do is that you have to draw this number space. Okay. X and Y and Z. And you have to say that let's consider a number space in which nx, ny, and z corresponds to the modes of vibration of atoms. If they ask why consider number space, why we are considering different types of modes of vibration, you can say that by device theory, the vibration of atoms is considered to be similar to the vibration of strings. So as for vibration of string, different modes of vibrations are possible, like n is a fundamental mode, first overtone, second overtone. Similar to that, the vibration of atoms also occurs in different modes. So here we are considering this n correspond to that quantum number. N is equal to 1 corresponds to the fundamental mode, n is equal to 2 corresponds to the first overtone, like that. So we are considering a number space. We are first deriving the density of states for phonons for 3D case. For 3D case, to find the density of states, we are drawing a number space and we are considering a spherical shell. Spherical shell. N is the radius of this spherical shell. Now let us calculate the density of states. For that, we have to write like this, G of n dn. So what does this mean? G of n dn means the number of states between n and n plus dn. So as I have already said, each point in the number space denote a quantum state. Each point have coordinates nx, ny, and z, which represents a particular mode of vibration of atoms which are lying along x-axis, y-axis, and z-axis. So each point in the number space signifies or represents a quantum state. Okay, so what we want to find out is what is the number of quantum states that lies within the volume of the spherical shell. Okay, so each point within the spherical shell represents a quantum state. So the number of states present within the volume of the spherical shell is simply the volume of the spherical shell itself, because each point corresponds to a quantum state. Is given by 4 pi. The volume is given by 4 pi n square dn, right? I think you know this. So then the number of states between n and n plus dn is equal to the number of points that lie within the volume of the spherical shell, which will be equal to the volume of the spherical shell itself. So it is given by 4 pi n square dn. Okay, but in number space, we do not need to consider the negative axis. As it is a number, there cannot be a negative number, right? Number of, the number starts from n is equal to 1 and n is equal to 2, like that. So there cannot be negative. So only we have to consider the first octant. Only one octant we have to consider. So we have to consider only one octant. And one more thing I need to tell you is that when a wave is present in the x-axis, it can, so this is x-axis, okay, and this is y-axis, and this is z-axis. So when wave is present along x-axis, okay, when a wave is present along the x-axis, the vibration can lie along y direction, or the vibration can lie along z direction, right? It can also vibrate in the z direction. It means that a wave lying along the x-axis can vibrate in the xy plane, or it can vibrate in the xz plane. So two types of vibration are possible for a wave lying along the x-axis. So here the degeneracy is 2. We are multiplying the degeneracy here into 2. So what we get is that pi into n square dn. So now we have to convert n to e, because we have to find g of e, right? So ultimately what we have to find is how g of e depends on e. So we have to convert this n with e. For converting n to e, we can use this. We know that e is equal to h nu, or nu is frequency, equal to h into v by lambda. And we know that lambda is equal to 2L by n, right? So E is equal to h v n by 12. Now we can write n as 12 E by h to L by h into velocity into E. So V is velocity, okay? Velocity here, V is velocity of sound actually. Velocity of sound. So n is equal to 12 by h in velocity of sound into E. We also have to find dn. So moving on to the next slide. So n is equal to 12 by h into velocity of sound into E, which means that dn is equal to 12 by h into velocity of sound into d. Substituting this value in g of n dn, we will get g of n dn is equal to pi into n square dn, right? Pi into n square dn is equal to pi into 12 by h into velocity of sound square e square into dn. dn is 12 by h into velocity of sound into d is equal to pi into 12 by h into velocity of sound whole cube into e square d, which means that g of e, which implies g of e directly proportional to e square. If we plot it, it looks like this. Negative energy is not physically possible, so it looks like this. Okay, directly proportional to e square. Now let's go to 2D case. 2D case. For 2D case, we just need to draw it like this. Each point in this plane represents a quantum state, nx and y. So we are considering a area like this, a circular region. Circular region like this. So we have to find the number of states, quantum states present within this area. Number of quantum states present within this segment of area is given by its area itself. Number of states present on this area on this segment of area is equal to the area itself, but as it is a number space, we can only consider the first quadrant. This one we cannot consider, only here. That is first quadrant. It's like this, 1 by 4 into 2 pi, n is the radius. N is the radius, 2 pi n dn into degeneracy. What is degeneracy? 2. So we'll get like this, pi into n dn. So we already know how to convert n to d. It is n is equal to 2L by h into velocity of sound into e, where dn is equal to 2L by h into velocity of sound into de. So putting in the values, we get g of n dn is equal to pi into n dn is equal to pi into, in place of n, put 2L by h into velocity of sound into e, dn 2L by h into velocity of sound de, which means g of e de is equal to G of E is equal to pi into 2L by h into velocity of sound whole square E. This is E, okay? E, which means G of E directly proportional to E. So it would be a straight line. It would be a straight. Now moving to 1D case. 1D case. Now, here also we have to consider only that one axis is there, right? Only one axis is there. And we have to find the number of states between this in this segment. So this is a segment of Dn. So we have to find the number of quantum states present within this Dn interval. So G of n Dn is equal to simply the length itself. What is the length? Dn is equal to 12 by h into velocity of sound into E. No, not E. So G of E dE is equal to 12 by h into velocity of sound dE. So G of E is equal to constant 12 by h into velocity of sound. Hence, it will not depend on energy. So the density of states for the phonons for 1D case is constant. It does not depend on energy. So that's it. So let's move on to the next question. Now the question is to derive the density of states of electrons for 3D, 2D and 1D case. Here instead of phonons, we have to find the density of states of electrons. So the method that we have to follow is similar to the method that we followed for phonons case, except now instead of considering the number space, here we are considering K space. So considering the K space, we can derive for 3D case. Kx, ky, kz. Here also we consider the spherical shell. Excuse my drawing, it is not good. Yeah, now K. K is the radius of the sphere, spherical shell. G of K dk, which means that the number of states which are present in the volume of the spherical shell between K and K plus dk is given by volume of the spherical shell, which is given by 4 pi K square dk. This is the volume of the spherical shell divided by volume of one quantum state. What is the volume of one quantum state? Is 2 pi by L cube. So this, I think you know about this. Say volume of one quantum state being 2 pi by L whole cube. Then if we are considering per unit volume, then this L cube will go. That is it will become 4 pi a square by 2 pi cube dk, because this L cube is actually volume. If we are considering considering unit volume, because density of states, we are considering unit volume, right? That L cube should go. Then it will become 4 pi k square dk by 2 pi cube. Then we have to convert k to e, as we did in phonon case. We converted n to e, right? Here we have to convert k to e. So how to do it? We have to know the relationship between e and k that everybody knows. E is equal to h cross square k square by 2m. So how do we get this relation? We know that energy is equal to kinetic energy plus potential energy for a free electron. On potential energy is equal to 0, which means that only kinetic energy is there, which is given by p squared by 2m. P is equal to h cross k, which means that E is equal to h cross squared k squared by 2m. That's it. Now, we can write k to be from this relation. We can write k is given by square root of 2me by h cross square. And dk is equal to square root of 2m by h cross square into 1 by 2 root e, just differentiate it, 2 root e dE. Okay. Now substitute it in the expression of g of k dk. We will get g of k dk is equal to 4 pi by 2 pi square 4 pi by not square 2 pi cube into k square 2me by h cross square k square into dk square root of 2m by h cross square 1 by 2 root e dE. I forgot to consider degeneracy here. So if we consider degeneracy also, here it will be look like this into 2, because there will be for each electron upspin and downspin are possible. So the degeneracy is 2. Into 2 into 2. So final expression looks like this. G of E dE is equal to 1 by 2 pi square into 2 into mass of electron by h cross square whole raised to 3 by 2 into square root of E dE, which means G of E directly proportional to square root of E. We can draw it like this. G of E E. So this will look like this. How to know how it looks like y, we can write G of E as y directly proportional to root x, which means y directly proportional to y square directly proportional to x. So the parabola will be along the x-axis. So here, so it will look like this. This is how the dependence of G of E on E looks like for TD case. For 2D case, let us draw kx and ky. Kx, ky. Let's consider this segment like this with the radius k. Okay. Then G of K dk. G of K dk is given by number of quantum states present within the area, this area segment between K and K plus dk is given by area, it's area divided by area 2 pi K dk divided by what is the area of one quantum state? It is given by 2 pi by L whole square. And we have to consider degeneracy also into 2. So if you are considering per unit volume, density of states, number of states, it is number of states per unit volume, right? So this L square has to be ignored as we are considering per unit volume. Then it looks like this. 2 pi K dk by 2 pi square into substituting the value of K and dk, we get some constant C into K. K is given by square root of 2me by h cross square, square root of 2me by h cross square into dk. dk is given by square root of 2m by h cross square, square root of 2m by h cross square into 1 by 2 root e dE. Then, which means G of E is equal to some constant C dash into root E into root E gets cancelled, right? So just a constant. So density of states for 2D case does not depend upon energy. It is constant. It will not change with energy. Moving on to the 1D case. 1D case, we have to consider a particular segment dk. Then G of K dk is equal to dk by 2 pi by L. If you are considering a unit volume, it will become dk by 2 pi. Then converting into energy, dk is equal to 1 by 2 pi into square root of 2m by h cross square into 1 by 2 root e dE, which is equal to some constant into e raised to minus 1 by 2 dE. So G of E directly proportional to e raised to minus 1 by e raised to minus 1 by 2. That's it.